Section 13.3, we're going to take a look today at something called dilations. And you guys see these all the time. In fact, you probably see this transformation more than maybe most of the other ones we've talked about, honestly. So to first talk about what it is, a dilation, also sometimes called a size transformation or scaling, is a transformation in which angles stay the same and lengths are adjusted by a fixed ratio. Because the lengths are adjusted, this is not an isometry. What was an isometry again?
Maintains length.
Yeah, it preserves length and distance, right? And this one will not do that, okay? If it does not change the distance, it's not a dilation. The pre-image and the image of a dilation are similar, but they are not congruent. Okay? So, the reality is what you're looking at right now is an example of a dilation. This is my screen, right? And this is the screen you're looking at. It's blown up, yeah? This is an example, and we're going to see a picture of one here in a second on my screen. This is an example of a dilation. It's a projection in this case. It's a projection. And so you've also seen ones probably where you have taken an image. It doesn't have to be taking an image and blowing it up. It could also be taking an image and shrinking it down. That's a dilation as well, okay? So, for example, this is the one I was going to draw a picture of, and I really tried hard to try and figure out how to get this image into your notes, and it just didn't happen. Every time I kept copying and pasting it, it kept disconnecting the projector into all the little parts. Like the circles and the rectangles and everything just disconnected every time I tried to move it from PowerPoint into Word. And that's never happened to me yet. So I decided that it was okay and you could just write down projector and it would probably be just fine. So a dilation has a center O around which the scaling happens and a scale factor which is bigger than 0. Technically the scale factor, yeah, bigger than 0, that's right. And it's not equal to 1. It's not written in there, I don't know why, but it should be. Write that detail down as well. A scale factor bigger than 0, and it's not 1. Okay, if the ratio were 1, the objects would be congruent, which means it's not a dilation. And that determines the amount of stretch or shrink. If the number is bigger than 1, it's a stretch. It actually enlarged the object. And if it were less than 1, still positive, but less than 1, it would be a shrink, and it would have contracted or shrunk the object. Okay? So here you can barely see it, but do you see my little corner over here? The little boy? Did you guys see him up there? This was the original that's going into the projector, and this is what it's projecting it into, and the scale factor on this particular one was a scale factor of 20. So it's 20 times as big as it was before. Okay? So here's our first example. We're going to describe the transformation of triangle ABC into triangle A prime, B prime, C prime. Now, in order to describe it, you have to do just this. You have to talk about what is the center and what is the scale factor. There's two pieces to talk about. This has a very similar feel to it as when we talk about rotations, right? To do a rotation, you have to talk about a turn center, and you have to talk about an angle measure, and then counterclockwise or clockwise. So here we have to do the center, and we have to talk about the scale factor. So taking a look at this one, what is the center of this dilation? Yeah, and it's not labeled, unfortunately, so let's just call it O, all right? So that we'll call it whatever you want. But so we have a dilation. With center O. And we have a scale factor. So look at it carefully. Can you tell what the scale factor is? Yeah, do you see the ratio? So if you looked at the length, let me get a color up here just a second. This will work. If you look at the length of this side of the triangle right here, it's 3. And if you look at the length of the larger triangle that it's projecting it onto, it's a length of 6. So it took all the side lengths and it did what to them? It doubled them. So we would say that that's a scale factor of 2. Okay, it doubled the lengths of the sides of the triangle. Notice it's always in reference to the lengths of things. When you double lengths, you don't double area. We'll talk more about lengths and area in chapter 14, but I just want you to be very, very clear that when you're looking at the size transformation, this sort of feels like it's doubling things, but the reality is that if you double the lengths of everything, you actually multiply the area by 4. There's 4 of those little triangles that'll fit in that big triangle, okay? So make sure you're looking at the side lengths when you're referencing the scale factor. For any dilation with center O and scale factor greater than 0, the following are true. First, the image of a line segment is a line segment, parallel to the original segment and r times as long. So I'm going to pause there and go back to the picture to show you what it's talking about. Those pink ones those ones I circled in pink, they're parallel, right? So that's important. The image better be parallel, the lengths themselves, to what you had before. And it has to be the scale factor times as long. So in this case, r times was 2 times as long. The second object, or the second piece of this says, the image of an angle is an angle congruent to the original angle. So we're not changing any angle measures. And because we're not changing angle measures, but we are changing side lengths, this means that the figures are similar. We say that two figures are similar. We did this before in another section. If it is possible to transform one onto the other by a sequence of isometries followed by a dilation. So the dilation is the enlarging or the contracting of the object. When it talks about this sequence of isometries, it means you might have had it also shifted around. So this creates a similar triangle, but obviously if I rotated the triangle, one of them or the other of them, they wouldn't change the fact that they're similar, right? And that's what that's referencing on that bullet point. All right, we need another picture. Okay, so I'm not going to draw this one in. I want you guys to try your hand at it. Hopefully you've got a pencil nearby if you're not already writing with one, so that in case you do make a mistake, we can erase it. This one wants you to find the image of a triangle ABC under the dilation with center O. Did the O come out okay on your notes? Okay, so it's right there and it looks like it's the center of the triangle as well, right? The center O and a scale factor of 1/2. Okay, so you're going to draw another triangle, still with the center O, where it has been dilated by a factor 1/2. So draw what you think that would maybe look like. Just try. And then I'm going to show you how you can think about it if you didn't quite have the right idea in mind. Okay, so is the triangle you drew inside the triangle that they originally drew? Good, because it should be. Scale factor of 1/2 means that it's making everything half as long, but it's still centered where it was originally centered. So it's almost like that you're shrinking it down. So you imagine, the shirt that goes in the dryer and it shrinks, right? It's really the same dimensions it was before, but just in a smaller, not the same dimensions, but the same ratio of the side lengths and everything. It's just in a smaller form, okay? So now the doggy can wear it or something like that. All right, so the original sides that's, excuse me, easiest probably to look at is probably side length AB, just because it's directly diagonal along these, dot grid. So it's 2 of these dot grid, diagonals, right? So if you're looking at that and you're shrinking it in, it's going to be right here. So that's the A prime, B prime. If you take a look along the side, we'll do AC next. It goes up 1 and over 2, correct? And it does it twice, up 1 and over 2. Kind of like calculating slope, Well, that's two of those sort of movements that we make, right? Up 1 over 2. Well, we're going to do the same movement, up 1 over 2. We're just going to do it half as many times because we're supposed to be doing a half of a scale factor of 1/2. So when we're doing that down here, I can take my point A prime that I just noted, and I can go up 1 and over 2, which puts me here. So my side length that I'm connecting is right here. I don't know why that's dotted, from a different class, I guess. Hang on. So there's my side length there. I'll make that one straighter here. Once you have two sides, you get the third one for free. So I'll connect it in there, but we can actually check and see that it actually makes sense and works too, right? So if we go from B up to C, we go over 1 and up 2, over 1 and up 2. I think I've almost got a Christmas tree kind of going on. And then if you do it from B prime to C prime, which I haven't labeled yet, you'd go over 1 and up 2, and you'd end up at that same spot at the top, which is called C prime, and now it's labeled. Okay, so it's shrunk, right? The original object has shrunk. All right, this one actually gives us the original object, and it gives us a image that's the final image. And it says to describe a sequence of isometries followed by a dilation, because you can do both, okay? Isometries followed by a dilation, so that the larger triangle, that's the blue one on the left, it's blue on my screen, it's kind of faded on your paper, I think, is the original, and then the final image is this, I think so, right? Larger triangle, oh no, it's the other way. The larger triangle is the final image of the smaller one. So we're starting with the smaller one here, okay? And then the larger one is our final image. Okay, so somebody tell me first what would have to happen. Isometries, so we'll do the dilation last. But what did we do first to get it to go and move toward where the final, I'm trying not to use the words.
90-degree rotation.
It's a 90-degree rotation. Now when we talk about rotations though, we have to have a center. So where is that center happening? Where's that rotation happening from?
About the point that has the 90-degree angle.
Okay, so the 90-degree angle. How about we label that? So if we put the point in here and we call it, say, A, then we can talk about it. It makes it easier to work with. So we first have a 90-degree. What was it, clockwise or counterclockwise? Counterclockwise. Counterclockwise. Rotation. Around, about, whatever word you'd like, around point A. Okay, so that's the first thing. That actually gets it in the right orientation, right? So if I rotated that 90 degrees around point A, the object will now be, I'll do it in yellow, here. Okay, that's the 90-degree rotation that you guys asked for. Now what would we have to do? I don't think we need a translation. We could do a translation, I just don't think it's necessary. We can probably do something else that will take care of it once, like with one more step.
Dilation.
We could do a dilation. Okay, so with a dilation, we have to have a scale factor and a center. What's the scale factor? We'll do the easy one first. That's usually the easier one.
Is it 2?
The scale factor is 2. And I think you could use either one of them, but either the vertical or the horizontal side lengths are probably your easier ones to see it on than the diagonal one. This one goes from length 2 to a length 4. This one goes from a length 3 to a length 6. It doubled it, right? So we had a dilation with a scale factor of 2, but we have to have a center of a dilation. Where's the center? It's still at A, yeah. So, Lauren, when you said we could translate it, we actually could translate it 2 to the left, right? So that we actually moved it over here to this corner, and then we could actually dilate from that point over. We could do that, but we don't need to because we can do it in a more concise way. Okay, so this would be, or this could be, one option. So this is sort of like step number 1. Step number 2 is that then we would have a dilation with center A. And scale factor 2. Now notice when you have a scale factor or when you have a dilation, there is a point on the dilation, if you're the center point itself, the point that you are dilating with respect to, that doesn't move, right? So when I'm dilating right here, this point A in the middle, it's a part of all those objects, right? Now, if you'll notice the very first image that we did, this one right here, the object that, or the point that we were using as our dilation point wasn't on the object, was it? So no points actually stayed in the same location. Did you see that? They all actually moved because the point was off of the object itself. Do you guys see that? But the distances stayed the same. I mean, the distances still doubled. Was this doubled? Yeah, doubled. So like this distance right here doubled in length to here. So the distances from the center of the dilation still doubled, but the object actually, it flat out looked like it moved that time, right? Whereas it doesn't almost look like in my dilation for this last one that the object moves, like at all. And the reason is because the point that we are actually enlarging it around, so to speak, is on the corner of the object itself. Now, this one had the part where we were enlarging it around in the center of the object instead of on one of the vertices, right? So that also made it look like it really like changed location somehow because the enlargement point was not on the edge of the object, it was in the middle of the object. So dilations can have sort of some different flavors of them. All right, last example, and it's a couple of parts to it. Consider the square OBCD with vertices 0, 0, 0, 2, 2, 2, and 2, 0. Perform a size transformation, and now the order of this happening is important. It tells you, first, part A, by multiplying the x and y coordinates of each point by 2, and then translating each point up 1. Okay, so the first thing I want us to do is to just write down our new points. We will draw the pictures in a minute, but let's just write down the new points that we have first. And we'll do it in a two-step process. If you don't need to see 2 steps, that's totally cool. If you do need to see 2 steps, then I'll have it written there for you so that you can. So we're going from 0, 0, 0, 2, 2, 2, and 2, 0. And the first thing we're doing is we're doubling each of the XY ordered pairs. So this is my doubling. So 0, 0, what happens when you double 0, 0?
Stays 0, 0.
Stays 0, 0. How about doubling 0, 2? 0, 4. Doubling 2, 2. 4, 4. And doubling 2, 0? 4, 0. Fantastic. Okay. The next thing it does is it says that we are going to translate each point up 1 unit. So how does translating it up 1 unit affect ordered pairs?
It's just going to bring it up 1.
But what is it going to bring up? I don't mean in the picture, I mean in the ordered pair.
The y coordinate.
Just the y coordinate. So I'm going to add 1, but only to the y value of each of my coordinates. So this is my up 1. So the 0 for the x value stays the same, and the 0 becomes 1. 0 for x stays the same, 4 becomes 5. 4 stays the same, and then the 4 becomes 5. 4 stays the same, and the 0 becomes 1. Okay, everybody good with that? We doubled, and then we moved it up 1. And we will call these new points O prime, B prime, C prime, and D prime. And we're actually going to graph them now. Okay, you've got 4 ordered pairs. If we did it all right, we should end up with a square when we're done. Right? Because these objects should be similar. When we translate and do all this and then we dilate, we should still have a similar object to what we started with, and it said it was a square to start with. So you can take your workspace grid here and you can draw this in. You'll have plenty of space, so you can kind of just put your axes wherever it kind of feels comfortable for you to put it. You've got plenty of space. Your object is supposed to go from, what were my points? 0, 1. So here's one of them. 0, 5. 4, 5. And 4, 1. So this is my square that I get. And this is O prime, B prime, C prime, D prime. Does yours look like that? Yeah? Okay, cool. All right, so that's object number 1 from part A. Part B says, I think it reverted this to say part A on my slide, but this is B. Okay, perform a size transformation of OBCD by translating each vertex up 1 unit, then multiplying the x and y coordinates by 2. So we're doing it in the reverse order, right? Okay, that's fine. We started out with those same 4 points, so I'm going to write them down again. I had 0, 0. I don't have quite as much space on mine. I think you guys probably have more than I do at this point. 0, 5. I didn't mean that. 0, 4, wasn't it? 0, 2. 0, 2, 2, 2, and 2, 0. Okay, so the first thing we're going to do is we're going to translate up 1 unit. So up 1 unit, did I read that right? Up 1? What is up 1 going to do again? Add 1 to the y value. So I've got 0, 1, I've got 0, 3, I've got 2, 3, and I've got 2, 1. And then what am I supposed to do? Double them, right? Okay, doubling 0 is 0. Doubling 1 is 2. 0, 6, 4, 6, 4, 2. And we will call each of these the same letters we had before, O, B, C, D, but we'll do double primes just to designate them differently. So this is O double prime, B double prime, C double prime, D double prime. And now we're going to plot these 4 points on our grid. Okay? And the same grid is fine. If it really bothers you and you want to draw the picture differently, you can, but I think it's probably going to be easier to relate the 2 objects if they're on the same grid when you're done. So the first point said 0, 2. The second one was 0, 6. The third one is 4, 6. And the fourth one is 4, 2. And if I connect those with my rectangle, and then I label them, if you have colored pencils, you could do like I did with my colors. That might be helpful. These objects, yeah, it kind of does. They're congruent, right? I mean, they're not just similar. I mean, they were similar to the original object I started with. The original object I started with, I didn't draw it in, but let me draw it in for you really quickly. The original object I started with is actually down here. If I put in my 4 coordinates, this is my original object. Okay? So it's not congruent to the original object because we did a dilation when we doubled things, right? But the 2 objects after they've been done these 2 translations and transformations to them, they do appear to be congruent. We have a square of side length 4. So what in the world happened? Why in the world? Because obviously what this means is that doing this in a specific order matters. The object is in a different place than it was if I did the objects, if I did the transformations in a different order. So transformations, sometimes anyway, are not commutative. All right, so those of you who've had me for either or other 2 courses, we talk about properties of whole numbers, and commutative is a wonderful property where it means that the order of something doesn't matter. The order of transformations, when we're working with dilations in them anyway, it matters, okay? So what in the world, why did it matter on this one? Why did I get a different location for my object the second time than I did the first time? What caused that? Why did doubling second shift it up 2 units?
If you're doubling a bigger number.
Hang on a second. Okay, so you're doubling a bigger number. All right.
You're doubling that, so that adds another one on.
It isn't exactly that it adds another one, but you're definitely on the right track. How much was our shift? Do you have an idea, Ashley?
Well, originally we were doubling 0, which stays 0, but then when we add 1 first, then you're doubling 1, so it's going to add 2 instead of just doubling by 1.
Okay, so the first time we shifted 1, correct? And the second time we shifted, it almost looks like we shifted 2, doesn't it? Why do you think it was a shift of 2? Because we doubled the shift, didn't we? Since we shifted first and then we doubled it, in essence, we doubled the shift that we made. Do you guys see that? The shift of 1 became a shift of 2 because the doubling happened second. So let's write down a few facts here. Can't remember if I have space over there. I don't really. I didn't here at the end either. Okay, we'll just write on this screen. Fit it in. You guys have space. The images are congruent. We've said that, so let's write that. But O double prime, B double prime, C double prime, D double prime is a shift up 1 from O prime, B prime, C prime, D prime. This is because the shift occurred before the dilation. Thus, the shift up 1 dilated by a factor 2 became a shift up 2. So if you don't take anything else away from this very specific problem, take away the fact that the order mattered, right? The order definitely mattered on which one we did first.